In our first series of videos, we laid out the basics of the Standard Model. Broadly speaking, the Standard Model represents the most fundamental particles with which all other matter is composed, and the facilities for interaction between such particles through the intermediaries of three of the fundamental forces of nature: electromagnetic, strong, and weak. Now, we want to discuss how physicists utilize the Standard Model to make predictions about the universe. The realm within which the Standard Model is applied is called quantum field theory. Before we get to there, however, it will be helpful to consider a more familiar area of physics known as classical mechanics. Classical mechanics involves the analysis of physical systems which are on the length and energy scales we are used to living in. For this reason, the complexities of quantum mechanics associated with the dynamics of individual particles are essentially negligible. They're simply so small compared to the system we are analyzing to be important. Ultimately, classical mechanics is only an approximation. The true physics of every situation must be described quantum mechanically because everything in nature is composed of the fundamental particles of the Standard Model. But, as it stands, classical mechanics is a really good approximation. Good enough for engineers when they design buildings and bridges, and even good enough to send men to the moon. Most importantly, the simplicity of classical mechanics makes it the perfect segue into discussing how physicists go about making predictions. All of classical mechanics can be encapsulated in a single question. Given information about where a physical system is and where it is going at a given time, predict where the system will be and where it will be going at all later times. To the uninitiated, this sounds a lot like fortune telling, and to a certain extent it is. But there's an important difference between a theoretical physicist and your local clairvoyant. The physicist is totally transparent about where his predictions come from, and in the world of classical mechanics, that means the principle of least action. To get straight down to brass tacks, nature is lazy. Or, to be kinder, nature is efficient. Whenever any system in nature needs to decide what it will do next, it chooses the option that minimizes this thing I call the action. So, what exactly is the action then? As you might have guessed, action is related to energy. On some level, we can think of it as being the total energy expenditure to go from one state of being into another. Strictly speaking, the action is given by an integral, or sum, over a mathematical functional known as the Lagrangian. The Lagrangian turns out to be, perhaps, the most important object of analysis in all of physics. Simply put, the Lagrangian of a given system is equal to the difference between that system's kinetic energy, that is the energy associated with the motion of the system, and that system's potential energy, that is the energy associated with the force field acting on the system due to the fundamental interactions and gravity.